All right, 1210 students. Here are some practice problems using calorimetry, um, heat of reactions, and just change in heat in general. Um, Starting with problem number 5. As a reminder, you can get these worksheets on Canvas. When you go to our Canvas homepage, navigate to the Modules tab, scroll down to the module that this is found in, which is Unit 7, and this is at the top of that module, along with, this is Module 8. So this is found at the top of the Module 8 bank, along with our other worksheet on enthalpy. Question 5 says, calculate the amount of heat associated. First of all, heat here, we're using Q. Associated with warming, a 456 gram sample, that's mass, of liquid water from an initial temperature, Ti, of 25 degrees C to a final temperature of 100 degrees C, Tf. With this information, Q is my unknown, M is given to me, and delta T can be solved for final temperature minus initial temperature. Since this is a warming, I should anticipate a positive delta T. That's positive 75 degrees C. That's the information given to me. When I look at my equations sheet to see what information I'll have available to me on the final exam, I see equations for Q, delta E with Q and W. I don't want this. I don't want pressure volume work. Here I have Q equals mc times delta T. That has a lot of the variables I know. And then I have the Q of a bomb. This is not a bomb calorimeter. So I can feel confident that the equation I'm looking for here is Q equals m times c times delta T. And luckily it's already set up the way that I want it to be. It's set up to solve for Q. But there is a missing variable, and that's C. This is something that will be expected to know here. This is specific heat because it's a lowercase c, which is different than heat capacity, which is uppercase C. And the specific heat for water is 4.184 joules. Or, in other words, 1 calorie, 1 small c calorie. Remember that we defined these as being the energy required. You know what? I'm sorry. I have to apologize. That is not, those are equal to each other, but that is not the specific heat. Specific heat has units of energy per gram degree C, calorie per gram degree C, or joules per gram degree C. That is the energy required for 1 gram of water to be raised by 1 degree C. That is a specific heat. So we actually know that value and we can plug it in. Q equals 456 grams times 4.184 joules for every gram being raised 1 degree C for a temperature change of positive 75 degrees C. This process is endothermic. We are warming the sample, so I want Q to be a positive number. Grams times 1 over grams, degrees C times 1 over degrees C, these should cancel with each other. I'm left with only units of joules, which is the energy that I'm looking for. And here we do just a basic calculator exercise. 456 times 4.184 times 75 degrees C. Here's one way to make sure that your number makes sense when you're putting this in. It takes 4.184 joules for every gram being raised 1 degree C. Well, I'm not raising it 1 degree C. I'm raising it 75 degrees C. And I'm not raising 1 gram. I'm raising the temperature 456 grams. So this should be a much larger number. The answer I get here is 143,092.8 joules. And of course, this number doesn't make sense to report. We should have reported this as kilojoules, which is 143. 0.092 if we're going to round to sig figs, let's say we get, let's just go with 3 sig figs based on the grams. We get 143 kilojoules. With that information, I can also calculate calories because I actually have this conversion. 4.184 joules is 1 calorie. And again, let's look at kilojoules into kilocalories. I know that's not what the question is asking for, but the numbers make a little bit more sense. 143 kilojoules, and there are 4.184 kilojoules in every 1 kilocalorie, lowercase c. Here I just take my number and I divide by 4.184. This gives me 34.2 kilocalories. Another way of saying that is 34.2 big C calories, because 1 big C calorie is equal to 1 kilocalorie. All right, easy. Now, problem number 6, an 876 gram chunk of aluminum was initially at 459 degrees C. That gives me temperature initial. This was allowed to cool to a final temperature of 23 degrees C. This process already should be an exothermic process. We're losing heat from the aluminum, the system, to the surroundings. The specific heat, lowercase c, is 0.215 cals per gram degree C. Pause real quick and look at the difference between the specific heat of aluminum and the specific heat of water. Aluminum takes less temperature to heat up, less energy, to heat up 1 gram by 1 degree C. Water takes a lot more energy. That 4.184 divided by 0.215, it takes 19 times more energy to heat up 1 gram of water by 1 degree C as opposed to aluminum. This might explain why you can heat up aluminum so fast and water takes a lot longer to heat up. Those are their specific heats. All right, question 1 asks, or A, calculate the heat capacity. This is capital C. Now, based on our notes, we have some equations for capital C. Capital C equals Q over delta T, the heat per degrees Celsius. Now, I don't have Q given to me in this problem. I do have the ability to solve for delta T, but I would need to solve for Q. Our equations sheet has this equation for Q, the one that we used earlier. Q equals M times C times delta T. But C here, little c, is not the same as big C. Heat capacity is how much total heat the system can hold. Specific heat is how much heat per gram degree C. You know what I forgot to pull out? We actually have mass given to us right at the beginning of this as well, 876 grams. That means that I have M, little c, and delta T given to me, which means that I could solve for C here. I could solve for Q. And once I solve for Q, I could plug it in. Why bother? Why don't we substitute Q and we get C equals M times specific heat times delta T over delta T. Now you should see that delta T cancels, and we can actually see that specific heat is equal to, heat capacity is equal to specific heat times the mass. Specific heat has units of joules per degree C, whereas specific heat is energy per gram degree C. To convert between energy per gram degree C and energy per degree C, I just need to get rid of grams. which means multiplying by the mass. So this is the equation that I'll use. The heat capacity is the specific heat times the mass. One more way to look at this. Specific heat is an intrinsic value. It only matters the type of material, not the amount. Whereas heat capacity is extrinsic. It matters how much you have. And if it matters how much you have, then you just multiply the intrinsic value by how much you have, and you get the extrinsic value. Okay, so let's plug it in. Heat capacity is equal to 0.215 calories per gram degree C, and my grams degree C is 439 degrees. I'm sorry, my delta T. Oh my goodness, what am I doing? My mass here is 876 grams. I get grams to cancel. I'm left with cals per degree C. My heat capacity, 0.215 times 876, 188.34 cals. If I wanted to report that, cals per degree C. If I wanted to report that in kilojoules, I'll need to multiply. If I want to report it in joules, I multiply by 4.184, and I get 788 joules per degree C. That is the heat capacity of this specific chunk of aluminum. Part B, determine how much heat. Okay, now we want to solve for Q is released upon cooling. I actually have two equations that I can solve for here. I could take Q equals heat capacity times the change in temperature, since I now know my heat capacity. Or I could use the same equation as before. Heat is mass times specific heat times delta T, all the same. So let's plug them in. Q equals 188.34 cal per degree C times 439 degrees C minus 23 degrees C. That is not the correct temperature. This was 459. If I were to plug this in, I would put into parentheses 459 minus 23 so that my order of operations is done appropriately. Maybe if I did this problem right, it would go a lot better. I haven't put in my values correctly. I have taken my initial minus my final, which is not correct. This needs to be my final temperature minus my initial temperature. Here's a way that we can check that. I recognized that this subtraction was going to give me a positive number, which would give me a positive heat, which would indicate endothermic. And we already described before that this should be exothermic because the block is cooling. Now 23 minus 459 gives me a negative number. So I'm going to plug this back in, substitute my numbers. You'll notice that it only changed the sign, which is exactly what I wanted. Q equals negative 82,116.24 calories. I'm left with, my units of Celsius cancels, I'm left with calories. This, of course, is negative 82.1 kcals. And we can solve for it from our other equation. Q equals the mass, 876 grams, times the specific heat, 0.215 cals per gram degree C, times delta T. This time I think I'll calculate delta T separately and plug it in. Negative 436 degrees C. Celsius cancels, grams cancels, 876 times 0.215 times negative 436 equals negative 82.1 kcals. If I want to convert this into kilojoules, I multiply by 4.184, and I get negative 343.5 kilojoules. Kcals to kilojoules, or I could have done cals to joules, but I cannot do cals to kilojoules quite as easily. Next problem. A 345 gram sample of aluminum was initially heated to a temperature of 325 degrees C. After it was dunked in 250 grams of water, initially at 25 degrees C, the final temperature of both substances was found to be 93.6 degrees C. Calculate the specific heat of aluminum. Now there's a hint here that says use multiple equations. I want to pull out some information. 355 grams of aluminum. I'm going to write that as mass aluminum equals 345.0 grams. Initially heated to a temperature, that's T initial of aluminum, is 325.0 degrees C. After it's dunked in 25 grams of water, I have mass water, 250.0 grams, which was initially at 25 degrees C. Initial temperature of water, 25.0 degrees C. The final temperature for both of them, they've reached thermal equilibrium, 93.6 degrees C. Now the question says, find the specific heat of aluminum. Well, I'm not given the specific heat of water either. What this looks like is the heat of the system should be opposite the heat of water. This is a calorimeter system, so I'm exchanging heat between the block and the water. So whatever the water is increasing by, the aluminum block is decreasing by. But we can actually take this equation, Q equals mc delta T, and we can elongate Q equals negative Q. We can say the mass of aluminum times the specific heat of aluminum times the delta T of aluminum is equal to opposite the mass of the water times the specific heat of the water times the delta T of the water. I know the change in temperature they both went through. I know the masses of both. And I know the specific heat of water is 4.184 joules per gram degrees C. I do want to point out that number is not on here anywhere, but it's very important to have. This is a number you want to keep close by when you're doing calorimetry problems. I want to solve for this. And this is the multiple equations that it's getting at. I know the equation for heat on both sides. I'm just substituting them in. So I'm going to divide both sides by the mass and the delta T of aluminum. That gives me this new equation. The specific heat of aluminum is equal to opposite the mass of water times the specific heat of water times the delta T of water divided by the mass of the aluminum times the delta T of the aluminum. Now I just plug it in. Specific heat of aluminum equals opposite the 250.0 grams of water times 4.184 joules per gram degree C of water times delta T, final minus initial, 93.6 minus 25. The water has warmed, so this is a positive 68.6 degrees C. Check that my units cancel to give me just energy. Great. divided by the 345.0 grams of aluminum times the delta T of aluminum. Oh, I made a typo here, which is my final temperature. 93.6 minus 325.0 is a temperature change of negative 231.4 degrees C. This is going to leave me with units of joules on top divided by grams per degree C on bottom. Those are units of specific heat. This is great. If you're like me, you might want to do these multiplications together, get two numbers, and then divide them. So 250 times 4.184 times 68.6, that's 71,001 joules on top. 345 times negative 231.4 on bottom gives me negative 79.833 grams degrees C on the bottom. Now I just plug this in. I apologize, my work is all over the place. The specific heat of aluminum is 71,001 divided by negative 79,833. Oh, I have made a mistake. I can't have a negative specific heat. I forgot that up top I also had this negative value. So I am dividing negative joules, negative heat, divided by negative. That gets me positive. So positive 0.889 joules per gram degrees C. Now if you're like me, you might be thinking, boy, in question 6 we had a very different specific heat. Well, that specific heat was in a different unit. So let's convert this unit and see if these two problems agree with each other. 0.889 joules per gram degrees C divided by 4.184 gives me 0.213 cals per gram degrees C. Not exactly the same, but within rounding error. Our last problem. A sample of calcium chloride that weighed 8.32 grams was mixed with 150 grams of water at 24.8 degrees C in a calorimeter that has a heat capacity of 92.7 joules per degree C. The resulting solution has a specific heat of 4 joules per gram degree C. If the heat of reaction of calcium chloride is negative 82.8 kilojoules per mole, what maximum temperature will the solution reach after mixing? We're given a lot of information here. Not all of it seems to go together. And there's some interesting terms here that we didn't quite see until the next module on enthalpy. But let's break this down. I'm taking a specific amount of calcium chloride. I'm mixing it into a solution with water at a specific temperature. We're given a heat capacity of the system, but we're also given a specific heat. Typically that means that we will use one of the two and not both. If the heat of the reaction of calcium chloride is this number, what maximum temperature? This means instead of using delta T anywhere, I'm actually going to be separating delta T into T final and T initial. I have T initial. I want to solve for T final. Here's where I want to start, which is if 1 mole of calcium chloride releases 82.8 kilojoules, then how much energy is released by this many grams? That means I need to start by going from grams of calcium chloride to moles of calcium chloride. Grams to mole conversion requires the molar mass. The molar mass of calcium chloride comes from our periodic table. Calcium with a mass of 40.08 plus twice the mass of chlorine at 35.45 gives me a molar mass of, I'm going to round this to say 101 grams per mole. Do I have 101 grams? No. So do I have 1 mole? No. So will I release 82.8 kilojoules? No. These should all be less. 8.32 grams. Put grams on the bottom, moles on the top. 1 over 111 grams per mole. And I'm actually going to add in here that 1 mole of this would release 82.8 kilojoules. I've just done dimensional analysis to take the mass of my calcium chloride and predict an energy that it will release. 8.32 times negative 82.8 divided by 101 tells me that this will release only 6.2. I should be allowed 3 significant figures here, so I'm going to round. 6.21 kilojoules. That is a value Q. So I can take this equation that we've been using, Q equals M times C times delta T, and I can break it apart to look for delta T. I get delta T equals Q divided by MC. I just divide by MC on both sides. And now I'm going to break this apart and say T final minus T initial equals Q over M times C, so that I can solve for T final. I'm going to add T initial to both sides. Q over MC plus initial temp. I have all of this information. T final is the heat, 6.21 kilojoules, that is released in this heat of reaction, divided by the mass. The mass here is of the solution because the specific heat I have is of the solution. So that is the 8.32 grams of calcium chloride plus 150 grams of water. That means that my mass is 158.32 grams. And together, this mixture has a specific heat of 4.00 joules per gram degree C. You'll recognize that this is not the specific heat of water. It's the specific heat of this solution. So I do not need the mass of water. I do not need the mass of calcium chloride. I need the mass of both. And I'll take this whole chunk, which will have a negative value, and I will add to it my initial temperature of 24.8 degrees C. If I'm doing this addition with degrees C, this needs to yield just degrees C. So let's make sure that my units cancel. Kilojoules divided by, joules. I actually can't do this conversion as is. I'm going to need to rewrite kilojoules. So I get negative 6,210 joules divided by the 158.32 grams times 4.00 joules per gram C, because now joules will cancel. Plus the 24.8 degrees C. On the bottom, grams times 1 over grams, so grams cancels. I'll be left with 1 over C, degrees C, which is the same as saying degrees C. So we plug it in. Negative 6,210 joules divided by 158.32 times 4 gives me negative 9.8, and I'll add to this 24.8, my final temperature with some rounding, let's say 15.0 degrees C. I've made a fatal error. If I find this answer on the test, positive 15 degrees C, with an additional answer on the test of negative 15, or perhaps a different number entirely, 9, let me say 9.8 plus 24.8. If I find an answer that is 34.6 degrees C, I may be choosing the wrong answer by saying 15 degrees C. Here's my fatal error. The reaction is releasing energy. So my solution will be increasing in energy. This is heat of the system, and this is heat of the solution, the reaction versus the solution. So this negative that I plugged in, I should have actually been plugging in as negative Q from down here, negative Q of the reaction. Since my Q reaction was negative, this should have actually given me a positive number throughout. So when I did this calculation before, should have actually got 9.8 plus 24.8, which rounds up to give me 34.6 degrees C. This is how challenging these problems are. That one sign change led me from believing that my temperature in the solution dropped from 24.8 degrees C to 15 degrees C. But I had to be convinced that the temperature of the water would not drop because it's telling me that calcium chloride releases energy. If calcium chloride releases energy, my solution has to be warming up. That was the fatal flaw that I caught right at the end. That led me back to say, if the reaction is releasing energy, then the solution is increasing in energy. Heat of the solution is equal to opposite the heat of the reaction. So I ended up with a positive 6.21 kilojoules. The solution is absorbing that from the heat of the reaction. My temperature increases. Be safe out there, chemistry students. These problems are not for the faint of heart. Recognize again that they gave us information that we never even used. It gave us a heat capacity and we didn't need it. You'll need to be cautious and careful. Be thorough in your math. Take a lesson from me and give yourself as much space to do these problems as possible. Do as I say and not as I do. This is a very crammed workspace. It makes it challenging if I wanted to go back and actually see my thought process. What I should have done was taken some sort of notebook in solving all of these problems, listed this as problem 6, and shown all of my work with as much space as I needed to make sure I was never confused and could always go back and check it. Keep working on these problems. Download this sheet after seeing this problem solved and try solving this again. When you've tried solving it, come back, see what steps you did right, what steps you got confused on. Then download it again, try it again, go to RealChem for more problems, go to the bottom of the modules on Canvas for more problems. Keep practicing. Happy studying.